Another tool we have to help us solve our quadratic equations is completing the square. Now we've already done completing the square 2 other times, when we were trying to rewrite the equation of a circle and when we were writing equations in vertex form. Here we have, if a quadratic equation is written in the form x squared plus kx equals d, where k and d are constants, then the equation can be solved by completing the square. Looking at exercise 4, we almost have an equation exactly in this form. The only thing that we have different is our a here is not equal to 1. Our a is equal to 2. And when you're completing the square, you need your leading coefficient to be 1. What we can do to fix that is we can divide each term of our equation by 2. My leading coefficient will simplify away, leaving me with 1x squared. 6 divided by 2 is going to leave me with 3x, and 3 over 2 is going to stay that way, or you can think of it as 1.5. And I'm going to leave a little blank because now we're going to complete the square, and remember, we're going to add whatever number we get to both sides of our equation. To complete the square, we take the coefficient of our linear term, which for us is the 3. Recall, what we need to do is divide this by 2, and then square our answer. So the number that I'm going to need to add to both sides of my equation is 9 over 4. Don't get scared that it's a fraction. Remember, we don't discriminate against numbers. The left-hand side, if we completed the square correctly, should factor into x plus 3 over 2 squared. Remember, it's the number you get when you divide it by 2. If you expanded this, you could verify that it will give you back this trinomial we have on the left. And on the right-hand side, we need to add these two numbers together. So if I want to add 3 halves to 9 fourths, I need to have a common denominator. So I'm going to multiply 3 halves by 2 over 2 to show that 3 halves is equivalent to 6 fourths. So now I have 6 fourths plus 9 fourths. I can add the numerators over the common denominator to get 15 fourths. Now hopefully you recognize this from the last video where I have one quantity that's squared by itself on the left-hand side and just a number on the other side. So I can utilize my square root property to take the square root of both sides. Now the square and the square root are going to kind of cancel each other out on the left, leaving just what was inside the parentheses. And on the right, I'm going to be left with plus or minus the square root of 15 over 2. Remember, when you have a radical with a fraction inside, you can look at the square root of the top and the square root of the bottom. So I just simplified the square root of the bottom. Now to solve for x, I need to subtract the 3 halves to the other side, leaving me with x equals negative 3 over 2 plus or minus the square root of 15 over 2. Notice these are our two solutions. Well, normally when we would be able to factor a quadratic equation, we get back two solutions. Not always, but a majority of the time. I think in our last example, we got x equals 6 and x equals 2. So in here, I would have x equals negative 3 halves plus the square root of 15 over 2, and x equals negative 3 halves minus the square root of 15 over 2. Also notice that since these both have the same denominator, I can write them together as one large fraction, where I have negative 3 plus or minus the square root of 15 all over 2. Since I got back kind of this ugly number that has this square root of 15 in it, that implies to me that if I would have tried to factor my original equation, it would not have factored nicely. So in other words, I would not have been able to find nice numbers to set up this product of two binomials. When you struggle with factoring an equation, right, you can't figure out what the two numbers are. Potentially, there aren't two nice numbers that factor this. So completing the square is always a viable option to solve your equation. Because even if you get down to the bottom and it's a nice number, all that means is that the original one did factor nicely, you just didn't notice it right away. So no matter what, you can use completing the square if you're going to get back really nice numbers, or if you're going to get back numbers that still have numbers inside of the radical. Another method we have for solving quadratic equations is called the quadratic formula. The solutions to the quadratic equation ax squared plus bx plus c equals 0 are given by x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now the quadratic formula is worth memorizing. In fact, many of you have probably seen it before, and maybe you have some ways of remembering it. I know a lot of people learn a song. I believe it's To Pop Goes the Weasel. Other people learn some sort of like a poem. I also learned kind of like a poem short story. So let me share that with you now. It says, a negative boy couldn't decide whether or not to go to a radical party. So he stayed home because he was square and missed out on 4 awesome chicks. The party was over at 2 a.m. So the negative boy refers to the negative b. Couldn't decide whether or not is our plus or minus. A radical party, some super old lingo here, just means like a really cool party, so that's our square root. He stayed home because he was square. Also old lingo, just means lame. And he missed out on 4 awesome chicks. Not very politically correct, but we'll continue. And the party was over at 2 a.m., which gives us that 2a in the bottom of our fraction. If that helps you memorize it, cool. I learned this when I was 14 and I still remember it to this day, so it worked for me, it might work for you. Let's try to solve a problem using the quadratic formula. So exercise 5. Notice that this equation is already set up in the proper form. I'm in ax squared plus bx plus c equals 0. That's really important to note because if you were given a quadratic equation that was not in this form, for example, let's say that the problem was given to us like this, I could not identify a, b, and c correctly until I move the 1 over to the left so that I'm in this form. I need to have my standard form for my quadratic equation before I identify a, b, and c. Otherwise, you might misidentify c as being positive when in reality c is negative. Now ours was given in the right form, so for us, a is 3, b is negative 4, and c is negative 1. Remember, our quadratic formula says our solutions x are equal to negative b plus or minus the square root b squared minus 4ac all over 2a. Or a negative boy couldn't decide whether or not to go to a radical party, so he stayed home because he was square and missed out on 4 awesome chicks. The party was over at 2 a.m. And we're going to substitute in our a, b, and c to the corresponding spots in the formula. So x is equal to negative 4, that's my b, plus or minus the square root of b squared. Well, that's negative 4 squared minus 4 times a, which is 3, times c, which is negative 1, all over 2 times a, which is 3. And now I can simplify. So negative 4 becomes positive 4. Negative 4 squared is positive 16. Negative 4 times 3 is negative 12, times negative 1 gives me back positive 12. And this is all over 2 times 3, which is 6. So I have 4 plus or minus the square root 16 plus 12 is 28, divided by 6. And now I'm going to use some rules that I know about simplifying square roots. So two numbers that I know that multiply to 28 are 7 and 4. And I also know that 4 is a perfect square. You can break up your square roots if they're being multiplied inside into two separate square roots being multiplied. And if I do that, maybe I'll notice that I know the square root of 4, right? The square root of 4 is 2, so I'm going to pull a 2 out. So I have 4 plus or minus 2 square root of 7. I don't know the square root of 7, so he gets to stay inside. And this 2 that I pulled out is from that square root of 4. Another thing that I noticed is I have even numbers. Here I have 4 and I have 2, and I have an even number on the bottom, which is 6. So all three of those numbers have a common factor of 2. Do not accidentally simplify before, like back up here with the 4 and the 6 and think, oh, they're both divisible by 2, I can divide by 2. You cannot do that until you've factored out a common factor from every term in the numerator and every term in the denominator. So I can't simplify just the 4 and the 6 because I didn't factor out a common term from this square root of 7 times 4. But now that I've pulled this 2 out, the 4 and the 2 have a 2 in common, so I'm going to factor that out, leaving me with 2 plus or minus the square root of 7. There's like an invisible 1 right here over 6. And now that I have my numerator as two things being multiplied, I can simplify with the 6 in the denominator, leaving me with just 2 plus or minus the square root of 7 all over 3. Discriminant. To determine the number of real solutions to ax squared plus bx plus c equals 0, evaluate the discriminant b squared minus 4ac. I hope you notice that this b squared minus 4ac is exactly what we have underneath the radical in our quadratic formula. So in our quadratic formula, this b squared minus 4ac is what's inside of our radical. Just thinking about square roots. If I have a positive number under the square root, that's totally fine. I can take the square root of it, and this plus or minus will give me two different answers. So if my discriminant is positive, then the number I have under here is positive. That's going to give me back plus or minus a number, or in other words, two real solutions. If my discriminant is equal to 0, that means that the number underneath my radical is 0, and the square root of 0 is still 0, so I'm going to have plus or minus 0, but if I'm adding 0 or subtracting 0, I'm not changing anything, so really this entire part of my formula is just going to go away, and it's just going to leave me with one answer, this negative b over 2a. So if my discriminant is 0, there's only going to be one real solution. And the last case is if my discriminant is negative. That means the number inside of my square root is negative. And we know that we have issues taking the square root of a negative number because it's not real. So if my discriminant is negative, there are no real solutions. Exercise 6. An open-top box is being constructed by cutting 3-inch squares from the corners of a rectangular piece of cardboard that is 5 inches longer than it is wide. We have a typo. If the box has a volume of 150 cubic inches, find the dimensions of the piece of cardboard. All right, so I'm starting with a rectangular piece of cardboard. And I'm going to construct an open top box. So I assume I'm going to have something like this. So I'm going to go from this piece of cardboard to some sort of a box. From this piece of cardboard, I'm cutting out 3-inch squares from the corners. So 3 by 3, 3 by 3, all the way around. I also know that the box is 5 inches longer than it is wide. So I have a relationship between length and width, and my length depends on the width, right? Because it's 5 inches longer than it is wide. So I'm going to let my variable be my width, and I'm going to define my length in terms of W, and I know it's 5 inches longer than that. Let's consider the left and right side to be our widths. So these are W, and let's consider the bottom to be the length. Remember, length is W plus 5. That includes the 3 inches, though, that I'm cutting from the corners, because I cut the 3-inch squares from this original piece of cardboard that was 5 inches longer than it is wide. So once I take away those 3 inches, this piece that's left here is going to be W plus 5 minus 3 minus 3. Minus 3 minus 3, or in other words, W minus 1. And same thing for my width. I originally had length W, but now I'm just going to have W minus the 3 inches from each corner, or W minus 6. So here's our setup. We have a big piece of cardboard, W by W plus 5, but I cut out these 3-inch squares, meaning that the little piece I have left are W minus 1 by W minus 6. Now, looking at our box that I drew over here, this front is our length. The side here is the same side we have here, or our width. And the height would be the same as this piece that I cut off, so that would be 3. I was asked to find the dimensions of the piece of cardboard, and I was given the volume. So if you remember the formula for volume, volume is length times width times height. I know my length, I know my width, and I know my height. So I'm going to substitute those into my formula. So my volume is equal to W minus 1 times W minus 6 times 3. I also know what my volume is, though. It says my volume is 150 cubic inches. So I really have 150 equals W minus 1 times W minus 6 times 3. I'm going to write the 3 in the front. And now I can either distribute all of this and then try to solve for W, or if I want to save myself just a tiny bit of time, what I'm going to do is I'm going to divide away this 3. Right, everything's being multiplied, so I'm technically dividing the whole side. And I'll divide the other side of my equation as well, leaving me with 50 equals W minus 1 times W minus 6. Remember, our zero product property only works if this number is 0, but for us it's 50. So we're going to have to do a little bit of work. So let's start by FOILing this out. So 50 equals W squared minus 6w minus w plus 6. Combine like terms, 50 equals w squared minus 7w plus 6, and I'm going to move the 50 to the other side so that I can have this set equal to 0. So now I have this quadratic equation, 0 equals w squared minus 7w minus 44. Let's try to factor this. My leading coefficient is 1, so this is the slightly easier case to factor because the first term for each of my binomials is just w. And now I need to find two numbers that multiply to negative 44, and they add to negative 7. Well, I think negative 11 and positive 4 will do the trick. So I have w minus 11 and w plus 4. Using my zero product property, I know either w minus 11 equals 0 or w plus 4 equals 0. That is, w equals 11 or w equals negative 4. But remember, we're doing an actual real-life problem, and w stands for the width of our cardboard. Can I have a negative width? I don't think so. So I'm going to get rid of this option because we don't want any negative widths. Okay, so we're choosing our width of our piece of cardboard to be 11. So if my width is 11 inches, I can find my length by using that relationship we set up. So remember, the length was equal to the width plus 5, or in this case, 11 plus 5. So our length is going to be 16 inches. So the dimensions of our piece of cardboard is 11 inches by 16 inches.